make that pull-out game weak. What's good, my statisticians? This is Professor Sampson from PS I Love Math, back with another statistical banger. I hope we finish all that probability stuff. So today we're going to start a new section, a new area. We're going to start talking about normal distribution. And we're going to start today talking about the standard normal distribution. So sit back, relax, grab yourself a cup of matcha, and don't forget to like, comment, and subscribe. And we out of here.
Hello, my statisticians. I am so excited. I cannot contain myself. This is when we start actual statistics. So you should have covered the normal distribution in a prior section. I'm going to cover the standard normal distribution. This is when we start talking about real statistics. And I know you're like, real statistics, what have I been doing thus far? You've been doing old stuff, you've been doing probability, but this is the beginning of statistics, and I want to make sure you have a clear background on it, because without this background, you will suffer through statistics. And remember, in my course, we will be using charts, so you will not be using the shortcut in your calculator. You will not be using the shortcut in your calculator of the normal CDF, normal PDF. You will not be using those functions in this class. So we will work through and find out how to go about using these charts. Like I said, I'm so excited about this situation. So let's get cooking on the information so we can jump right into it. So as I said, you should have just finished talking about the normal probability distribution. So the normal probability distribution was cool and all, and the situation was that it took a long time for mathematicians and people to keep doing the z-score like you did, trying to find it for every individual z-score there was to have. So every time you had to do a problem, you had to go back to doing the z-score. What happened was mathematicians came up with a way to standardize it so you wouldn't have to do that much work. They started off with the fact that if you recall, the second property of a normal curve, what it said was the normal curve is completely defined by its mean and standard deviation. So that's what the normal curve is defined by. What we want to do is we want to standardize it, make it something that we can use to compare, also without having to do one for every kind of problem you could possibly come up with. So that's how it started. The important thing about this section also is for you to understand that area of under the curve and probability are the same thing. Let's write that down. I wish I could write it down in big old capital letters. So before we start here, we want to put this out there that area under the curve and probability are the same thing. So if a question asks you, what's the probability of this? Or what's the area under the curve? They're asking you the same question. So make sure that you know that so you're not confused. So let's get back to the standard normal distribution. So the standardized distribution is called the standard normal distribution. It's a single curve used for reference that has basically improved inferential statistics by folds and folds, by a whole lot. Again, because it allowed mathematicians and people not to have to do so much work. So the standard normal, we standardize everything. For the standard normal, remember the standard normal, you had your standard deviation and then you had your mean. So for the standard normal, we say that mu, the mean, is equal to 0. We're standardized for everything. And then we said the standard deviation, sigma, is equal to 1. That's what we would do when we have the standard normal, okay? So the standard normal distribution is a normal distribution with a mean equal to 0 and a standard deviation equal to 1. So there are a couple of properties that you want to know in reference to it. So the properties are as follows. First property is that the standard normal distribution is bell-shaped and symmetric about the mean. It is bell-shaped and symmetric about the mean. So we're not talking about skew left, skew right. We're not talking about anything. We're talking about it as bell-shaped. The second property we just went over, just rewrite it, is that mu is equal to 0, that the mean is equal to 0, and sigma is equal to 1. The third property is that the total area under the curve, under the standard normal distribution curve, is equal to 1. Remember, the total area under a curve is equal to 1. Why? Because what's the total probability? Probability probability is equal to 1. The last property is that the x-axis is a horizontal asymptote or the standard normal distribution curve. I'll write that down. Now, this is really an algebra or a calculus thing, this fourth one, but you just need to know it. So these are the properties, and if we need to, we'll get into them in more detail, but just so that you know them. This standard normal distribution, we call it a z-score. Remember, we covered z-score already, and we already know the general z-score formula, right? Z is equal to x minus mu over the standard deviation. So that's the formula for the standard normal distribution. The standard score, called a z, so we call it a z-score. We might call it a z-value, but it's a z-score. And if you recall, a z-score is what? 2 decimal places. We learned this in our class back in chapter 3. So let's talk about how we standard score. Remember, another recall is, what was the definition of the z-score? The definition of a z-score is a number which indicates how many standard deviations a data point is from the mean. So the z-score is the z-score is a number that indicates how many standard deviations a data point is from the mean. So how do we find these z-scores and what do we do with them is the next thing, and how do we just go about standardizing. So let's give a quick example here. If you had mu is equal to 65, sigma is equal to 20, and x is equal to 40. Remember, you cannot write this formula the way you want to write it. The formula is written x minus mu, not mu minus x, not highest minus lowest, because you can get negative numbers. Remember what the z-score is: distance from the mean. And the mean can be anything, and you can be below the mean or above the mean. Out of 40 minus 65 all over 20. Negative 1.25. So you should be drawing a picture. So you're 1.25 standard deviations below the mean. We're going to talk about the most important thing, I think, in this particular area: using standard normal distribution tables. Around the 19th century, tables were created by mathematicians. Around the 19th century. Around the 19th century, tables were created by mathematicians to keep people from having to do this calculus all over. Because sometimes you guys want to understand, I don't understand this. Where do these numbers come from? What is this? This stuff actually has a basis in calculus. You don't have to understand that because you're in a stat class, where that would be outside what we're going to be doing. But still, this all came from calculus. So like I said, around the 19th century, tables were invented so that the calculus that you needed to find the area under the curve, that no one had to keep repeating the calculus all over and over and over again. All you needed to do was to be able to read the table. Now, there are different types of tables around that were created, but what we use is known as the cumulative normal distribution table. Again, this lecture may not be for you if your teacher or if your school allows you to use a calculator, because we will be working strictly with the tables. You will not be using the shortcut in your calculator that says norm CDF or norm PDF. So we're just going to be working with this cumulative normal table. Let's take a look at this cumulative normal table and just go over what it looks like before we do any problem. The table looks like this. Now, remember when we talked about z-score had to be 2 decimal places? This is why. The inside of this table is area under the curve. And in this case, it's area under the curve to the left, area under the curve to the left. All of these inside pieces are area under the curve. Now, remember, there's a positive z-score and a negative z-score. I just took this excerpt from the positive z-score, but then there's another side for the negative, which I'll probably show you a little bit later. This is it. So all of the interior stuff is area under the curve. Let's see, how do we meet around it? You see the z-score here. This is how you read it. Remember those 2 decimal places? If the z-score was z equal to 1.25, and they ask you for the area under the curve, let's just say to the left, and it will be written like probability. Let's just write it right now. The probability that z is less than 1.25. Let's just write it out. Let's just call it what we should call it and keep it moving. What is this going to be? Z is less than 1.25. Now it's cumulative, so it's understood that it's less than or equal to. So less than 1.25. So how do we read this chart? This is the tenths place, and the top here is the hundredths place. So to read this chart, you got Z is less than 1.2, and then 5. Where's 5? Over here. Everybody see that? 1.2. I'm going to try to make my line all the way across. And here's 5. So that will be your answer. So 1.2 with the 5 at the top. So your answer to the question, what is probability that Z is less than 1.25? That's going to be equal to the left, less than left, is equal to 0.894. This is how you read the chart. It's not difficult. Remember, the outside are the z-scores and the inside is the area. I could have also given you 0.894 and asked you for the z-score. So for example, if I gave you that the area under the curve was, let's say, 0.9750, you would have to look inside of these areas, find 0.9750. The area is 0.9790. What is the z-score? It can go backwards or forward. So I would look through this whole chart and I would see that 0.9750 is right here. So that's equal to a z-score of what? 1.96. So that z-score is equal to 1.96. That's how you read the table. That's why you had to have your z-score written in 2 decimal places, because the chart is 2 decimal places. And when you're comparing later on in the semester, you need to have 2 decimal places to compare it. So this is how you read the chart. This is an important part of this video. You need to stop, pause, make sure you understand where all of the numbers are coming from before you go on to the next part. So now let's jump right into some problems here. I'm going to say find the area of the standard normal curve to the left. Let's say Z is equal to 0.74. So what is the area under the curve for Z is equal to 0.74? So you have to look on your chart. Scroll through your chart, look for 0.74, which as you can see on my chart, 0.74. Now you have to learn how to read your chart here. Is 0.7704. So you should get that. You should be able to see that 0.7704 by going down 0.7 and over to 4, 0.74, 0.7704. You should be able to see that on the chart. If not, pause and then go back to it. Let's say Z equals negative 2.16. What's the area under the curve to the left? So we go look for negative 2.16. You see right here, negative 2.1 over to 6. So negative 2.16 at 0.0154. Should be reading along with your chart. 0.0154. So Z equals 1.02. You go to the chart, look up 1.0. Now see, that's the negative side. Make sure you go to the positive side. 1.02 is 0.8461. To be following along with me with your printed out chart, 0.8461. The next thing we want to do, let's say if we want to know the area under the standard normal curve to the right, Now your chart doesn't start reading something differently. And again, some of you can check in your calculator and make sure that these numbers are correct, but your calculator will give you a different answer. Let's do an infomercial here. Oh, hell no! I'm telling you that you must use the chart. Some of you will try and use the calculator because you have it to get over. However, the calculator is more precise, meaning the calculator is more accurate than a chart. Remember, the chart only has 4 decimal places. So the calculator is more precise. So the calculator may give you 0.7705, which would be incorrect. I would know at that point that you use the calculator instead of the chart. So you are using the chart. Now, if you know how to use the calculator, which I'm not teaching for this section, then you can check and see if your answer is close, but do not use the calculator. The norm, CDF, or PDF function, do not use it. But we know that area under the curve is a total. It's the total area under the curve. So the left plus the right, remember, the total area under the curve is equal to 1. Just like we said, remember, area under the curve is the same as what? Probability. So probability is what? Equal to 1. So if you want to get the right side in your algebra manipulations, like we did before, it's going to be 1 minus the left side. Now, there is another approach. There's another approach in the book, but I don't teach that approach. If you want to use it, that's fine with me, but that's not the approach that I'm going to teach. Anyway, we want to find the area to the right of this, the area under the curve to the right. So let's say Z is equal to negative 1.55. Right? Z is equal to negative 1.55. So let's look that up. So as you can see, negative 1 on your chart, 0.55, 0.0606, 0.0606. Now, will the chart naturally give you the right side because that's the question? No. So in order to get your right side, you're going to have to do 1 minus 0.0606. And that is going to be the area to the right. So your answer is 0.9394. So that's how you find the area to the right. Remember, the chart is only going to give you area to the left. Even if you ask for area to the right, the chart is only going to give you area to the left. I will explain the other way. The other way is knowing that your chart is symmetric. Remember, that was our first property, that your chart is symmetric. So technically, if negative 1.55 is 0.0606, and positive 1.55 is 0.9394. So you can get it that way. That's the alternate method. So if I look up positive 1.55, you see I will get 0.9394. That is the alternate way of doing it. However, there are other charts that lean a particular way that are not symmetric. So that's why I teach you to know whether the chart is saying it's left or right, so you know what to do. Since the z-score is symmetric, this works. You will get another chart. You will get another chart in a couple of chapters that's not symmetric. So you have to know how to do the left-right thing. So that's why I don't teach it that way, but you're free to do it that way if you like. I will never teach it that way. So let's go through it again. You're looking for area under the curve to the right. So let's say if Z was equal to 0.32 and you're looking for area to the right, you go to your chart, 0.32, look that up. Looks like 0.6255. So you need 1 minus 0.6255 to get your area to the right, and that is equal to 0.3745. So that takes care of when you're looking for the left or the right. Now you may have some problems that ask you to find the area in between two z-scores. So find the area under the curve that lies between two z-scores. So let's say, for example, you have z equal to 0.75 and z equal to 1.70. So you're really looking for the area in between. So if I was going to draw a picture, and drawing a picture works for a lot of students. So let's go to our chart and find out what Z is for 0.75. Sometimes I do this. So now I'm going to go look up Z equals 0.75 on my chart. 0.75 is 0.7734 and 1.70, 0.9554. And the area in between them is the difference between these two, but it's always the highest, then minus the lowest. For obvious reasons, it's area. So area can never be what? Area can never be negative. It has to be between 0 and 1. So you're going to take 0.9554 and subtract 0.7734. And that's going to give you the area between these two. So the area in between these two will be 0.2220. Don't forget your 0. Remember, this is probability. Let's say you have negative 3.27, so z equals negative 3.27, and we're still talking about the area in between, and z equals negative 1.44. Again, go check out your chart and read your chart. I'm going to read mine in my hand so I don't have to flip back. Looks like 0.0005. and negative 1.44 is 0.0749. Of course, you have to subtract the two, 0.0749 minus 0.0005, and put that in your calculator. I'm not switching back to the calculator. 0.0744. The last type of question that you'll have, the area outside. Now, I do this type of problem a different way. So this is for areas outside of the intervals. Again, I do this a different way. So they'll ask you to find the area under the standard normal curve that lies outside the intervals given. So you will be given z is equal to, let's say, negative 1.11, and z is equal to 3.21. Now again, the book or your instructor may do this differently. I like to continue what I've been doing. Now let's recall real quick up here, I had, let's say, negative 3.27, right? And negative 1.44. Have my curve like this, and I was looking for the area in between, which is what I found, right? The area in between. Now, if we were to draw this, it will look a little different. I will still have my, let's say, 3.21, and these are not drawing the scale. And I would have, let's say, my negative 1.11. But now I'm looking for area outside, right? Makes sense? Outside of these intervals, not inside. But remember, the total area under the curve has to be 1, right? The total area under the curve must equal 1. So this is the way I'm going to do it. The book shows you how to add them together. I do something a little different. So I actually follow the exact same thing, so I don't have to keep remembering. See, the thing is, you always have to remember new stuff, I continue the same way that I find inside. I do that the same way for finding the outside. Your book will do it differently, but I like this way. So I still look up z is equal to negative 1.11. So do that. I have is 0.1335. Then I'm going to look up 3.21, and I got 0.9993. I do the same exact thing as I do for area in between. I take my 0.9993 minus 0.1335. Remember, so I don't have to remember new skills. Oh, I didn't remember how to do that. I didn't remember how to do this. So I'm going to subtract my 9993 minus the 0.1335. Following along, make sure I'm right. You should get 0.8658. Now remember, 0.8658 is what? That's going to be this. 0.8658 is that, right? Because that's what we have been doing. That was the area in between. I'm not looking for the area in between. I'm looking for the area on the outside. But to find the area on the outside, remember, area under the curve has to equal what? 1. So this inside area plus the outside area have to be equal to 1. So to find my outside area, I'm just going to do 1 minus 0.8658. And I'm going to get 0.1342. So this is my answer. This is my answer to the area outside, because the area under the curve has to be equal to 1. So I do it this way. The book does some, and other people do some adding, some addition part. I don't do that because I know that whether I'm doing inside or outside, I'm going to do them exactly the same way. But only when I go to do outside, I have to do 1 minus the inside. Again, this is the way that I do it. This is the way that I choose to teach it. Let's do one more of these outside areas. Because again, the way that I show it is going to be pretty simple because it's nothing that you haven't done. So let's try this one. Z is equal to negative 1.93 and Z is equal to 0.59. Okay, same thing. I'm going to my chart, negative 1.93. I have 0.9732 and then 0.54. That's not right.
And
I could exit out, but I'm not going to. I'm going to just correct my error right here. Negative 1.93, and I should know negatives are small, 0.0268. I was looking at the wrong side of the chart, and I wanted to keep that error in there to let you know that you need to make sure you're looking at the right side of the chart. But so you know, the positive chart side of the chart is 0.5 to 0.999. The negative side of the chart is 0.0 to 0.49, whatever. That's how I knew that it should have been wrong. Anything negative is going to be between 0 and almost 5, and anything positive is 0.5 and above. So this negative 0.59 is equal to 0.7224. Okay, again, I'm going to subtract the 2. That's going to give me the inner. So to subtract the 2, you should get what I get, 0.6956. And then since I'm looking for the inner and not the outer, I got to do 1 minus 0.6956. And the answer is 0.3044. So this is your final answer. Usually that's it, but in the book that I'm using, which might not be everyone's, they have some fancy schmancy type ones that I just want to go over just one example of it. And this book is saying it wants you to find, it gives you Z1 is equal to negative 2.31. Then they give you a Z2 is equal to something else, 1.67. And the question says they want the total area. And what is total? Everybody should know the total is a sum. So they want the total area that's to the left of Z1 and to the right of Z2. Don't get this confused. It's the same thing that we've been doing. You know that the table only reads left, so this side is cool. You can read this right off the table, 0.0104. Now they want to the right of 1.67. So I'm going to look on my chart for 1.67. So 1.67, I look at my chart and I get 0.9525. Why did I write that up there? Because that's not the right answer. Remember, this is area to the left. Remember, your chart only reads area to the left. So in order to get your area to the right is 1 minus 0.9525. So that area is going to be 0.0475. So they want the sum of these areas. So you can have 0.0104 plus 0.0475. And then you add those together and your total should be 0.0579. Chart only reads area to the left. Anything else to get area to the right is 1 minus area to the left. That's about it, no matter how they try and throw it at you. That's about it for this section that I've been excited about. We'll work more with the chart in the next section. Don't forget to like, comment, and subscribe, okay? And this is Professor Sampson from PS I Love Math, and I'm out of here.
Don't get me wrong.